All right. Hello, everyone. Welcome back to CS560. So I have received some emails about the first quiz because some of you joined the class later from the wait list. It's okay for the first quiz if you submit it after the deadline. I will still count the 1 point for the first quiz. Okay, and we haven't yet finished the first introduction lecture quite yet. There is a part for revealing the mathematical knowledge that will be needed basically throughout the whole course. So today we will spend like 10 to 15 minutes on the rest of these slides. And the new slide for the new module that we're going to cover today. Yeah, the first quiz is the syllabus quiz. Okay. So yeah, there will be some new quiz questions for the lecture today. Okay. So now I'm going to wrap up the introduction from where we stopped last time, and then the new module that I have already created on Canvas is called Getting Started, and I also uploaded the slide handout for the new content today. All right. So there's quite a bit of mathematical knowledge that will be needed. So let's go through it one by one. It's basically some concepts and notations. Okay, so sometimes to get familiar with the notations is a first step towards understanding some complex equations or concepts. Okay, so first of all, the floor. So it's when the floor symbol applies to some real number, it means that we just toss the parts after toss the decimal parts. So 1.5 becomes 1, 2.6 becomes 2. So it is the largest integer less than or equal to x, right? And also ceiling, it is the smallest integer that is greater than or equal to x. Okay, so these notations applied to a float number or to a real number converted into some integer number, and this way is usually this method is usually used when we want to when we do not want to be as accurate. We don't want much accuracy, but we think that a approximated integer is sufficient for our analysis, and these floor and ceilings will be quite useful. All right, and modular arithmetic. Okay, so it's basically deals with when you divide in two integers. Okay, and say you want to divide an integer a and by a positive integer n, then the value a mod n. So if we write this notation a mod n, it is the remainder of the quotient a divided by n. Okay, so this modular operator is very commonly used. Is very common in a lot of most general programming languages, and in most algorithm implementations, it's quite oftenly used as well. Okay, so the mathematical relationship can be described by this equation using the floor ceiling, the floor symbol, which we just defined previously. Okay, so this module, the remainder part is always a positive number, a non-zero number, but it should be smaller than the number n. Okay. So this modularly equal notation here means that the a and b have the same remainder when they are divided by n. But this is something that you want to know. For now, we may have a chance to use it in some of the assignment questions. All right. So secondly, on this slide, we're going to look at the exponential functions. Okay, so so this is the basis for forming the concept of something we call a series, number of series, geography series. So that's a good question. Are we going to use these for proofs? Depends on the question. So it's very rare that in one proof question we're going to use everything everything that we talk about today. But really, kind of different questions have different required knowledge based on the topic. Okay. So for the exponential functions, some basic relationships shown in these slides are useful. So the relationship, for example, a to the power of n and raised to the power of n again, we will can swap the numbers, the exponential terms here. Okay. And also, it's important to know that this function, the exponential function, a to the power of n, is monotonically increasing, and also it increases really fast. Okay, if you plot the curve for this function, you will see that the curves increases at the beginning. It increases quite slow, but as long as the n grows larger and larger, the curves become really deep. So really steep. So it's a kind of a property that we will use when we compare several functions that are all monotonically increasing. But the speed that they increase are different. Some increases faster, some increase slower. And from the perspective of so if our goal is to pick a function that grows slower, then it'll be helpful if you plot those curves, how the functions increase with the input variable. Okay. All right. So when the base of the exponential function is the number e, and then we can use this e to define a set of special functions. Okay, for example, the natural logarithm function, the base here, the function e to the power of x can be defined by this series, and it's an infinite series. And the denominator, if you look at it, it uses some other functions like called the factorial function, which we will review in the next slide. Okay, so don't worry if the y is not shown here. Okay, we don't actually need to prove y e to the power x is a summation of this bunch of terms, but it's just for preparation, so that it might appear in the future lecture content showing some proof steps. Okay. And also, we can rewrite this function into this limit formation. Okay, like if you push n to the limit of infinity, then this whole thing 1 plus x over n raised to the power of n is essentially this e to the power of x. Okay, so this is something we should know about, but don't need to know how to prove. Okay, so based on the natural, the base of the natural logarithm function, we can look at the logarithm, more generic logarithm functions alone. So these logarithm function to compare with the previous slides, this slide is more important because when we describe the running time of algorithms, we basically use mathematical functions to describe the running time. And we know that functions changes with input. It can grow with input or decrease with input. But for the algorithms, if we let the input, the size of the input to be the input number, then the function usually grows. Okay, so that means for larger inputs, the time for handling that inputs with the same algorithm will be bigger, will be longer. It will take longer time than processing shorter inputs. So the running time of an algorithm is basically always increasing. But as we said before, the exponential functions increase really slow. And if you plot a linear function, the linear function increases really steady. Okay, and ideally, we would like to see some logarithm functions, because logarithm function is a function that grows rather slow. And in terms of running time, this is good news. Okay, it means that the cost of solving some problems will not be infinitely big when the input is very large. Okay, so that's why we will deal with a lot of logarithm functions when we discuss the efficiency of algorithms. Okay, so on this slide, it's basically we have some basic definitions for what a logarithm is. So given a logarithm function, we need to pay attention to two parts. First of all, it's the base. Okay, the base is written here. Sometimes we can ignore the base by default if we think of the default base is 2 or the default base is e. Okay, so these are the default modes, but usually we should consider the base. So the log to the base b of x is written in this form. So the meaning is that if we raise b to the power of y, then we will get x. And y can be described by this logarithm term. All right. So that's a logarithm function. So it's also, so as we said, it's a strictly increasing function. But good news is that it increases very slowly. Okay. So anyway, for larger inputs, the outputs would be larger. So these equations hold if the x1 is greater than x2. Okay. And the special case for logarithm of 1 is 0. Okay. And for logarithm functions, we have this principle called combination rule. So if we take the logarithm of a product, then we can decompose it into the summation of two individual logarithm terms. Okay, which is also useful. And the logarithm of an exponential function is something we can remove the exponential term outside the logarithm function. So it becomes a times logarithm base b of x. Okay. So, and in a special case where the base is 2, then we can use the shorter term LG. But in some places, people use different conventions. Some people would assume that if there's no base, then the base is 10. It depends on the different conventions it is in different disciplines. In computer science, because people are more used to a binary number, so when we ignore the base, we usually refer to the logarithm of base 2. Okay, and for the another shorter usage, ln, it means the logarithm of a natural base. And for that, I think most disciplines have the same conventions. All right. All right, so the last property that I'm going to show here is the some other tricks of logarithm function. The first one is called, if we can add the third base. If we got logarithm base b of a, then we can basically rewrite this whole thing into the logarithm of base c of a divided by the logarithm base c of a b. Okay, and this property, so using this form, we can change the base of logarithm from one constant to another. So if it's useful to our goal of proving something, okay. And the next one is also a switch of base. So it's actually not a switch of base, but it's a switch of positions of within an exponential functions. So if we raise a to the power of some logarithm function, then we can switch the c and a's inside. So the c inside out and the a inside the logarithm term. Okay. So these are the tricks that might be useful in the future, just for in case you are get warmed up at the beginning of this semester. Okay, so I think we have several slides to go. So for these slides, we have factorials. So we use the exclamation symbol to indicate factorial. Okay, so the factorial of n is actually the sequential products, or a sequence of products from 1 to n. If you use 1 times 2 times 3, until n minus 1 until n, that is how you define the factorial. And this definition is a kind of recursive definition that we will see a lot throughout this semester. So we use these curly brackets to define two conditions. And the first condition tells us the value of this function in some boundary condition. So this if n equals 0, it's a boundary because n cannot be smaller. N should always be greater than or equal to 0. So in this boundary condition, we will define the value of this factorial, which is 1. Okay, so it's kind of a special case because we got to have some boundary. Otherwise, the function is not defined, is not well defined. And in other cases, in other non-boundary or what we call recursive cases, then we can define the function's value recursively. Okay, so by recursively, we are actually using we're actually calling this factorial function again. Okay. Yeah, I think it's a typo. So why is it fx? So it actually should be n here. Okay, I will fix that later. Because the input is n. So actually, within this case, we are calling this factorial function again. So with inside, we can write it as fn minus 1 times n. Okay. So within the definition of factorial, we are calling the factorial itself again. So this is something that's we call recursive in computer science. All right, so factorial, which we already saw in 2 slides ago when we defined the natural base of natural logarithm, right? We will use it very often in the future. Okay, then in the last 2 slides, we'll look at the permutations. Okay, so it's a permutation is an operation defined on a finite set. Okay, it's an ordered sequence of all the elements of S, and with the constraint that each element only appears exactly once. Okay, so if we have 3 elements, A and B and C, then the permutations have 6 possible outcomes. There are 6 permutations in total. Okay, listed as above. Okay, so we basically can use the factorial function to count the total number of permutations. Okay, and that also has its statistical basis. So it's a problem of choosing elements or picking elements out of a set, right? So for the first element, we have n choices, and after one element is gone, then we have n minus 1 possible choices again. So we need to use multiplication to combine all these possible choices. Okay, and a k permutation is basically a subset of the permutations. So we are not choosing all the elements to make the reordering, but we are just choosing a small subset. We're just choosing k out of n, and with the same constraints that each element only appears once. So with this k permutations, we can use the permutations formula like this way, by n times n minus 1 times n minus 2 until n minus k plus 1. Okay, and if we use it defined by the factorials, it's also in a neat form. Okay, so that's permutations. And corresponding to permutations, we have combinations. So the only difference is that the sequence of elements in combinations doesn't matter. Okay, and so that means the combinations is a smaller quantity. Okay, because the same set of elements, but in different orders, they are treated as the same combination. Okay, in this case. So like in this 4 element set from A, B, C, D, then there are in total 6 2 combinations. But if you think about 2 permutations, then AB is different from BA. But in combination, these two are the same combination. Okay. So the formula for K combination can be derived from the permutation form with a larger denominator, with an additional term here with K, the factorial of K, because we are ignoring the K factorial possible numbers of reordering, possible numbers of sequences, different orders within that K elements. Okay. All right, these are the bases for combinations and permutations. Okay, so it takes longer than I expected to finish all of this. All right, I think we have 2 more slides to go maybe. So this is a compact form of writing, taking K combinations out of the set of n elements. All right. So now let's talk about series of numbers. So there are 2 types of series. First, let's look at arithmetic series. So which is a simple example, plussing, like summing up 1 to n. Then we can basically use the formula to compute a summation. And we will immediately see it in the example for the insertion sort algorithm that we will analyze today. Okay, and based on it, it's the sums of squares and cubes, and we can memorize it. We don't need to memorize it, but it's just for the reference of future usage. And another more commonly used series is geometric series. So we use the exponential functions to define this series. So for geometric series, it also has the formula for computing the summation of all the elements in it. Okay, and this formula is well known for cases where x is a number between 0 and 1. And in those cases, when n approaches limits, infinity limits, then the numerator will be gone when n is sufficiently big, right? Because a number is smaller than 1, when we take the exponential functions of it, it approaches 0. Okay, so these two are the most commonly used series. And harmonic series, it's not that often usage, but we may have a chance to see its application once in the semester. And for integrating and differentiating series, it's also another special application. It's like when we already know the summation, for example, the summation of a geometric series, then we can, if we have another series, which is the result of taking the integration or taking the differentiation within each term in that series, then we can directly take the summation form and directly apply the integration or differentiation onto that summation form. Okay, so the example is like when we know that the summation of x to the power k in this form is in this, can be expressed by this compact form, then what about if we want to know the summation of these series? So inside each term, the k times xk is basically the result of taking the derivatives of the previous series, geometric series. So the same would apply if we take the derivative on the summation term. Okay. So this is a special case of application. I think we may have a chance to use it once. All right. All right, and that's pretty much of it. And we won't use everything all at once. In one example, but some cases are really quite frequently used in this whole semester. For example, logarithm function and geometric series. So these are all quite useful knowledge to get prepared with. All right, and that's it for the introduction parts. I will pause the recording. All right. So, yeah, so we will get started. So we will have a taste of how an analysis of algorithm will be conducted using sorting algorithm as a typical example. Okay, so the sorting problem that I think we have a sentence covering introducing what algorithm is in the last lecture. So an algorithm needs to take something as inputs and generate some outputs. So in this simple case of sorting algorithm, the input and output are all sequence of numbers. Okay, so what an sorting algorithm does is to produce some reordering of the input sequence so that the output sequence is in order, either in descending or in ascending orders. Okay, so when we analyze an algorithm, a sorting algorithm, we first care about it should be correct. Okay, so a correctness is easy to check, right? You just go through all the elements for once. If there is at any position, the decreasing or increasing rule is violated, then it is not an accurate, not a correct algorithm, right? So more importantly, we also care about the running time, because it takes different amount of time if we implement algorithms differently. Okay, if you don't carefully implement the algorithm, even the sorting algorithm will cause you a lot of running time. Okay, so we basically want to show how different ways of implementation will result in different running time by using insertion sort and merge sort as two examples. I think we will have the time to cover the insertion sort today, and we will introduce the conventions for the pseudocode. So this is the first time we saw the pseudocode used in this course, and we'll look at the we'll know about what each keywords in the pseudocode convention means, and we will stick to those conventions because we'll use these conventions to implement everything covered in this course. Okay, and more importantly, we will introduce a scheme or we'll introduce some techniques to analyze the running time of the insertion sorts. All right, let's get started. Okay, so given such an inputs, for example, we have n numbers from A1 to AN, and we want a permutation of the inputs such that the first element is the smallest and the nth number is the biggest. Okay, so we can use a intuitive way to think about it, because we all played the playing cards game. Well, I assume that we all know how to play a playing card game, right? So we usually want to sort a hand of cards, right? And let's think about the scenario. Like we start with our hand empty, okay? And we have a pile of cards facing down the table. And then what we do in the game is that we take turns to take one card at a time from the table. And then what we do is to insert that card taken into the correct position in our hand. Okay, and eventually we will get a handful of cards in the sorted order. And each time, each insertion, we need to find the right position. Okay, and we basically is to compare the one card in our right hand with each card in our left hand, and find the correct position and insert that card into the hand full of cards. Okay, so the insertion sorts is can be described by this playing cards analogy. Okay, so I have a demo video it's basically a demo using cards as an example, but I don't think we need to go through it because we will directly go to the algorithms to see how it works. Okay, if you're interested, you can watch the video later. Okay, so let's read the pseudocode first. All right, so this is how most of the algorithms in this course will look like. We will start with the algorithm's name as the first row. It's called insertion sort, okay, in capital letter. And within the parentheses, we have the inputs parameter or input arguments that we called A. Okay, so this letter A is the inputs. So it's an array of numbers. So on the leftmost column, we see the line numbers from 1 to 8. So these numbers indicate the line number. This is the first line, second line to 8th line. And with that number, we can count how long the algorithm is. Okay, and also we have these indentions. Okay, so these indentions indicate the code structure. Okay, so the indention from line 2 to line 8 indicates that this body of code from line 2 to line 8 is within the scope of the for loop. Okay, the for loop starts from the first line. The first line indicates, it defines the range of the for loop. Okay, the for loop will iterate from 2 to the length of a, which is the last elements of the input array. Okay, and this variable j is what we call a loop counter. Okay, all right, and there's another indentation within the blue part again. So this indentation is kind of embedded into the for loop's body. So because it indicates a secondary indicates a secondary loop, which is a while loop. Okay, so this while loop, if we look at the scope of it, it's already embedded inside the for loop. Okay, so this kind of structure is what we call a nested loop structure. So it's a while loop in for loop. In other cases, it can be a for loop in another for loop. Okay, it doesn't really differ essentially, but it's an embedded. So basically, this embedded structure, when you notice that, you will see you basically need to realize that, okay, for each iteration of the for loop, the whole while loop will get executed once. Okay, so that is something we can immediately think of. All right, so that's something we can directly see. And if there's anything else we should pay attention to, then it should be this line. This third line is a special case because it uses with double slash, which means this is a comment. Okay, so this is something we write when we want to indicate, when we want to inform the readers of the code what the function is. Okay, so the comment line is not executed at a runtime. Okay, so right now it's just something we can visually done. We can visually have an intuition of what this code looks like. Then let's get into the steps of analyzing the function of it. So it basically takes an input of n numbers, and we are supposed to sort all these n numbers. And what we can know is that this algorithm has a property called in place. Okay, oops, it's an in place algorithm that will change the values of elements within the input array A. Okay, and it will cause changes to the elements in A, and so that it doesn't need to return anything. Okay, there is no return statements. No, we don't need to return a new A or something. Okay, so this is not something that is always necessarily true, because we can write programs that doesn't change the internal states, or it doesn't change the elements of the inputs at all. And in some programming paradigms, which we call functional programming, we kind of prefer those paradigms that don't change the internal states, that don't change the elements within the inputs, because that is much safer. It doesn't cause untractable changes in the program. And this in-place change is very often commonly seen in imperative programming style. Okay, but it doesn't matter a lot in this course, because it's about the efficiency that we care most, but not the efficiency in terms of programming. We're actually cares about the efficiency in terms of runtime efficiency, but not about the maintenance for software or maintenance for algorithms. Okay. So let's start with a stepwise analysis. Okay, so given the inputs, let's see what it will do. Okay, so let's have a random sequence of numbers from 5, 2, 4, 6, 1, 3. That is 6 numbers. So we'll use different colors to indicate the positions of the loop counter, because we know that the loop counter j starts from 2 to a dot length. Okay, so here there's something that we didn't say explicitly. So the index of the elements in that array starts from 1. So I see a question. It is supposed to be 1. So it is true that the first elements has the index 1. Okay, so that is what we assume. And the last elements has the index a dot length. So this is the convention that we stick with within this course. Okay, so we know that in some programming languages, or most programming languages, the starting index is 0. For example, in Python, we want to access the first element in the list. We just use index 0. Okay, but because this is pseudocode, and maybe the author of the textbook want to make it easier to read for people not that familiar with programming languages, then anyway, the convention that we use in this textbook use the index 1, like the first element has index 1. So let's see, because you have questions about whether it should be j equals 1 and 2, right? So we can analyze step by step to see if that is the case. Okay, that convention hurts. That's all right. You will get used to that. I think there will be one more exception when we talk about linear time sorting algorithms. And in that case, we have we indeed had a 0 index case. Okay, but trust me, it doesn't. It will not have bad effects on how the algorithms can be analyzed. I think it will make things quite clear. Really doesn't matter whether the first index is 0 or 1. Okay, all right. So let's see why it should be from 2 to a dot length. So one thing we can guess is that because there's inside I equals j minus 1, right? So the consequence of j starts from 1 is that if we compute 1 minus 1, then I will be an index 0. So then a of 0 is not well defined, not well defined in this convention, right? Because following this convention, we must have all the indices should be greater than 1, should be equal to or greater than 1. So that is partially why the j starts from 2. Okay, and let's use the black background, the dark background, to indicate the position of the loop counter j. Okay, so that's where j initially starts with. It points to the elements 2, second element. So within the body of the for loop, what it does is to assign that current aj to the variable called key. Okay, so we have something key which has the same value as a of j. So key is something that we need to compare with all the elements before aj. Okay, and we need to insert these aj into a correct position somewhere before the aj. Okay, so that's why we need to start from a position that is before j, which is j minus 1. Okay, so we will let I to be the starting position of the while loop. Okay, and the while loop will end with the condition we'll continue executing with the condition that I should be greater than 0, and also the elements AI should be greater than the key. Okay, and we already know that the key has the same value of AJ. Okay, so let's look at the first iteration again. So in the first iteration, J is 2, and I will be 2 minus 1, which will be 1. So what we are doing here is to compare with AI and the key. Okay, so AI is 5, and 5 is greater than the current key, which is 2. So that means the condition of the while loop is true. Okay, so that means the body of the while loop will be executed. Okay, so let's look at the body of the while loop at line 6. So what it does is to assign AI to AI plus 1, okay, which basically moves AI to the element that is right next to it, right? Moves the AI one step to the right, and then it will decrease I to continue the while loop. Okay, and after the while loop is ended, we will assign the key to the position of I plus 1. Okay, so after the while loop is ended, in this case, the key will be assigned to A1, which means 5 and 2 will be swapped. Okay, so that is the result of after the first iteration of the for loop. All right, then the for loop continues. Okay, we are only done with one iteration of for loop, and the second for loops in the second iteration of for loop, J will be 3, and J will point to these third elements in the input array. And accordingly, I will be 3 minus 1, which will point to the second element. Okay, and this time the second element will be compared to the key, and it still holds that 5 is greater than 4. So the line 6 will be executed again, and this 5 will be moved one step to the one grid to the right, right? And the key will be copied to this position, to the second position. Okay. So that's the second step, second iteration is done. And we're gonna do this for the rest of the elements. And in the case of the third iteration, it's kind of special because this time the key is 6, okay? And if we look at the new value for I, it will be 3, right? But if we compare A3 here, the value of A3 is 5. So 5 is smaller than 6, right? Which means this condition is not satisfied, right? We will only execute the body of the while loop if these two conditions are satisfied. But this time, the AI is smaller than the key, which breaks the rule. So that means there's no need to do the swapping. There's no need to move around the 5 to the right because it's already smaller than the key. Okay, so there's no need to move the key around. Okay, so we will do nothing in this while loop, and we'll move on to the next iteration. In the next iteration, the elements we've got for the key is 1. Okay, and now it becomes interesting because 1 is a very small number. So when we compare 1, the new key, with all the elements ahead of it, we will always do the swapping. Because 6 is greater than 1, it will be moved right to it, and 5 is bigger than 1, it will be moved one grid to the right, and so as to 4 and 2, until the last step is reached where the I hits 0, because this is another ending condition for the while loop. Okay, so at this step, when I decreases to 0, the while loop will end, and then we will assign a key to the current position, which is 0 plus 1, which is A1. Okay, so as a result of this iteration, we will have 1, 2, 4, 5, 6, the first 5 elements sorted. Okay, so similarly to the remaining elements, this same procedure will go on until the last element is processed. Okay, so the last element is 3, and we need to compare it with all the elements before it until we find the correct position to insert it. And eventually, we will have some outputs that looks like this, from 1 to 6 in sorted order. All right, so that is a complete example of how the insertion sort algorithm runs. All right, and I think the procedure tells the name of the algorithm. It's a continuous comparisons before the key elements with a bunch of already sorted elements, and then find the correct position to insert the current key, yeah, until everything is sorted, everything is compared and sorted in this algorithm. Yeah, we need to know the time complexity of the insertion sorts, and next we're gonna move on to that analysis. Okay, so because we have 20 minutes, 25 minutes left, less than 25 minutes left, I think I'm gonna, after we finish the slide 6, we are gonna finish analyze some running time of it. Okay, all right. So if we, yeah, the key is a temporary variable that is only used within this for loop. Okay. All right. So if we connect to the analogy of the playing cards example, right? So within any iteration of the for loop, we have AJ chosen as the current card to be inserted. So you can think of the role of AJ as the card to be inserted. And the position, the elements from A1 to J minus 1, these cards are the cards that's before AJ. So they constitute the already sorted cards. Okay. So then the remainder parts from AJ plus 1 to N, they are kind of the remaining pile on the table, and their orders are unsorted. And each time we just take the top one of it as our AJ and try to insert it among the already sorted cards. Okay, so here we can know that for sure that the cards or the numbers from A1 to J minus 1, they are the elements that are originally from position 1 to J minus 1, but they are in sorted order now. Okay, and this property is something we called a loop invariance. Okay, so this term loop invariance will be used to analyze the correctness of a loop, or it will be used to analyze an algorithm, the correctness of an algorithm that's has a loop structure involved. Okay, so but I'm gonna skip the loop invariant analysis for now. First of all, it's optional to this course. It's a very strict technique to analyze, to kind of prove that an algorithm is true, which is not required by the course. But I think if we have time on Thursday's class, we can do this after we are done with the time analysis. Okay, I think we care more about running time efficiency, right? All right. And pseudocode conventions. Yeah, let's start from here. Let's proceed on a little bit quickly. So if we look at the code, we don't have keywords like begin, end, or we don't either have curly brackets, right? We kind of follows the pseudocode kind of follows the convention, programming convention for Python. We use indentions to indicate code blocks. Okay. So there are some keywords: for loops, while loop, repeat, until, and the loop counter. In this case, the j will retain its value. Okay, and also immediately after the loop counter's value is the value that first exits the loop counter, the loop bound. Okay, so in this case, after the loop, after the outside for loop is ended, the value for j would be a.length plus 1, because it's the immediate value that exits the loop bound. Okay, and also we use 1 indexes, as we mentioned before. Okay, and also we can use the in this convention we used attributes of the objects. In this case, it's the a.length, and the length is the attributes of an object a. All right, this slide 11, I'm going to skip it. Okay, it's not important for now. Okay, so let's look at the efficiency of an algorithm. So we need to first lay out a bunch of definitions. So in order to analyze the resources that an algorithm causes, we can think of memory, communication bandwidth, hardware, right? But most importantly, we care about computational time. Okay, so in order to analyze the time, we need to have a model of a computer, and this model is rather simplified. So we assume there's a one processor, and with random access machine model, random access memory model. So in this model, there's no like parallel computing fancy stuff going on. Okay, so that means the instructions will be executed one after another. There's no concurrent operations. Okay, so and we will consider a set of primitive instructions like the adding, subtracting, multiplying, dividing, flooring, sailing stuff, and other data movements like loading, storing, copying, those and other control stuff, controlling code like if, else, function call, return. So all these instructions, they are primitive instructions, which means they will cost a constant amount of time. Okay, and also which means their costs are acceptable, are not insane amount of time. So if now we are going to analyze the running time of insertion sort, it actually really depends on the inputs. Okay, because it's an easy question. It takes longer to sort longer input arrays anyway, right? So we actually need to find a function that defines how the running time will grow with the size of the inputs. That's really the key property we want to define for insertion sort. Okay, it doesn't well, knowing that a input of, say, for example, 100 elements, if we know that it costs 100 seconds, or 50 seconds. But it doesn't really help too much if we don't know about a general function that describes the mapping relationship, right? We also want to know what about the input grows to 200, what would be the new running time, right? So it's really the function that we should use to describe the running time of an algorithm, okay? And this function is takes the inputs, takes the size of the inputs as inputs, okay? All right, so now let's further define running time and the input size carefully, okay? So the input size is usually the number of items, okay? So in this case, it's the number of elements in the input array. And for running time, it's a little bit trickier, okay? And we will use the number of primitive instructions or steps executed within the algorithm, okay? So the notion of step is a machine independence concept, okay? It has nothing to do with how fast a computer runs, okay? So if we refer to the previous slide 12, we have a bunch of primitive instructions defined, right? So basically, all the operations involving arithmetic operations, data movements, like copying the value from one variable to another, and the if-else condition statements, they are all primitive steps, okay? And we can assume that they cost constant amount of time. All right, so based on these assumptions, we can try to define the running time for each line of code in the pseudocode. All right, so we assume that the ith line takes ci amount of time, okay? Because let's use c to indicate a constant, okay? We don't know the specific number, but we know that it is some constant, okay? And there's another quantity, which is the certain number of times for each line being executed, okay? So these second times, it's an integer number. It's not the same thing as this ci amount of time. So this ci is a number, is kind of the number of, is the actual cost for one primitive operations. And the second quantity is the how many times, or it's a count. It's a count of how many times that each line is executed, okay? So one is a constant and one is the integer numbers. So these are something we need to consider separately. So under this analysis framework, now we put the code here. What we're gonna do is that, okay, we can first put all the constants here, okay? So this is something, the column here is what we called the cost, okay? So the cost for the first line is C1, second line is C2, and we notice that the third line is 0 because this is a comment, and the comment is not executed, okay? So we have C1, C2 to C8. So this is the actual cost for executing each line once, which are constants. And the second quantity is the number of times that, how many times each line is executed, okay? So we list the number here. The first line of code is the for loop statements. So what this for loop does, what this for loop statement does is to increment j after each line of code, after each iteration is ended, right? So because the range of the for loop is from 2 to n, right? We assume that the length is n, okay? So it will range from, iterate from 2 to n, and that is n minus 1 numbers, okay? But since after the last iteration, the j will increment by 1 again in order to break the loop. So the total amount, the total number of executions is n, but not n minus 1. Okay. But for the other code within the body of the for loop, the number of execution times is n minus 1. The line 2 will be executed for n minus 1 times. So is line 3, so is line 4, so is line 8. And we didn't write from line 5 to line 7 because these 3 lines have another loop involved, which makes things more complex. Okay, but that doesn't mean we cannot deal with it. Okay, we need to think about another way to count how many times each line of those while loop code has been executed. Okay, so because we don't have further informations, we have to make some assumptions. Okay, and we can assume that for each loop of the outer for loop, for each iteration of the outer for loop, j, it ranges from 2 to n, and the while loop test is executed tj times, and j is the subscript tj, because this quantity tj is related to j. It's different. The value of tj, the value of tj's are different in different j's. So t2 can be different from t3, can be different from t4. Okay, but it is unknown. It is something we don't know. So we use some variable tj to indicate the case. Okay, so with tj used here, then the total number of times that a while statement is executed can be expressed by this summation. That is for sure, right? Because the j, as the for loop says, the j will iterate from 2 to n. And in each iteration of the j's for loop, the while statement will be executed for tj much times, tj that many times, tj times. So if we sum up t2 to t3 to tn, we sum up all the t's, that will be the total number of execution times for the while loop. That makes sense, right? So have tj defined, we can replace those question marks here with some expressions of tj. Okay, so with expressions like tj here and the summation of tj minus 1 here and tj minus 1 here. Okay, there's tj minus 1 with the same reason as we have shown here, right? Because the loop statement is always executed one more time than the body, because we need to break the for loop. Okay, so the while loop's body here for line 6 and line 7, they are also executed one less time than the while loop head statements. Okay, all right, so now having these column defined and also the first column defined, we can use these 2 columns to define the total cost of the algorithm. Okay, which is simply the sum of running times for each statement executed. Okay, so now if we look at the first line, executing once will cost us C1. And we know that it will execute n times. Then what will be the total cost for line 1? We should use C1 times n, right? And for the second line, it will be C2 times n minus 1. And for line 3, line 4, and for all of those lines, we'll need to use the constant cost times the number of times in order to get the total cost. All right. So if we combine all these terms, okay, it will give us a rather complex terms. Okay, it'll be something like C1 times n, oops, C1 times n, C2 times n minus 1, C4 times n minus 1, plus C5 times this big chunk of summation, C6 times this chunk, C7 times this chunk, C8 times n minus 1. Okay? So it looks complex, but actually it can be simplified because you see these are just the linear terms which can be combined with these terms. Okay, and the thing is that we don't know about TJ yet, so these are what we're going to deal with, right? We want to have more information about what TJs are. Okay, so in the next slide we will analyze what TJ would be. Okay, so let's we have 3 more minutes to go. I think we can finish these slides. Okay, so so let's think about the best case for the insert and sort. Well, for a sorting algorithm, the best case is that it's already sorted, right? We don't need to do a lot of work. So we basically, the best case is that if the input is already sorted, then when we compare the key, which is AJ here, we will find that all the elements before AJ are smaller than itself, are smaller than AJ, which means this while loop will immediately break, right? Because all the numbers before J are smaller than the key, smaller than AJ. So the body of the while loop will be never executed. And that means the while statements will only execute once for each time, right? So that means TJ equals 1, and it remains 1 for all J's. That is the best case. And in that case, the T of n will simplify to this form, which is a bunch of constant times n. Okay, and we can rewrite it by combining all the coefficients here. So it's a linear function. Okay, and we can further simplify it as a times n plus b, which is a very nice, neat linear form because the total running time of the algorithm is linearly or grows linearly fast as the input size. And in a concrete example, if the 100 element takes 50 seconds, then the 200 elements, we can infer that it must take 100 seconds also, right? Because it's a linear function, and which is good news for us. But that good news doesn't always happen to us because we are only analyze the best case where it's already the input is already sorted. So the worst case is that the input is not sorted at all, or like it's basically inverted. So we will leave that to the next our next lecture, our next meeting on Thursday. Okay. So I will upload the video later to YouTube and publish on Canvas. I think there will be another quiz question related to the mathematical introduction part today. Yeah. Thank you everybody for coming.
Professor, I have a question.
Yeah.
I don't know if you mentioned this before class, but did you ever figure out about those of us who are on the wait list and trying to get into the class? Do you have any more information about that?
So right now the class is very big, and I don't think I'm going to add more students to the class.
Okay.
Yeah.
So
sorry
even if we're like third or fourth on the wait list, you're not going to add any more students?
Sorry, I cannot. I won't be able to do that. I already increased the class.
Okay, thank you.
Yeah, no problem. All right. Any other?
Professor, is there a quiz after this class?
Yeah, there will be one quiz.
Will it be due like today or like?
No, not today. The quiz usually due in 2 days.
Oh, it's gonna be like that all semester?
Yeah. That's correct.
Okay, thank you. Oh, and were you able to revise the assignment list and the due dates and all that stuff? I remember asking you last class.
Oh yeah. So for that, I will need a little bit additional work on that. And do you think? Yeah, I would like to bring that into discussion. Maybe. Do you think to have a fixed deadlines for all assignments? Would you prefer that, or sometimes, because depending on our progress we're making, some assignments may have flexible deadlines?
I mean, that could work. I just wanted an idea of how much I was gonna be able to how much we were gonna do this semester.
Yeah. So we will basically have 8 assignments.
Mm-hmm.
Yeah, and each would consist of 2 or 3 questions.
Okay, thank you.
Yeah.
Professor, are there any office hours like for the TA?
We usually have TA office hours, and I am in a way to in the progress of discussing it with our TAs.
Okay, thank you.
Yeah. Okay. All right. Thank you for coming. I'll see you on Thursday.